1, 2, 3. All right, less than 5 minutes per problem. Let's race through this stuff. What? All right, for the circuit shown below, E equal to 20 volts, L is 4 millihenries, and R equal to 5 ohms. After steady state is reached, so steady state, you close the switch, the current rises. This is not part of the circuit. The current rises in this, but the steady state current is just E over R. Okay. So in this circuit, it's E over R. Immediately thereafter, S1 is open, S2 is closed, and S1 is open. Then you open S1, meaning removing the battery, and close S2. But remember, energy was stored here, so that will drive a current through here. Okay, and so I'm sorry? Yeah, right. We do. It's just that I'm trying to figure out. Okay, so we'll open this and we'll close this, and I'm trying to figure out which direction will the current move. Well, you could pick to make the problem easier. No, it's not. You could have it move either way. Yeah, because it moves in the path of least resistance, but in this case it's equal, right? Yeah, no, but in a physical circuit it'll move one way. I don't know the answer to that. Okay, I'll have to. So I imagine it'll probably move this way. It'll go around clockwise. Okay. Anyway, I'll have to look that up.
We could assume that since the inductor would be fighting the growing current, the top would be positive and the bottom would be negative up until you close the second switch and open the first one. Because the whole time it would have been fighting the initial battery, right?
No, okay. So the current is flowing like this.
Yeah.
You shut off this current.
Yeah. So the top of the inductor should be positive at that point, right?
Yeah. Okay.
Science.
That's right. Okay. So what Fred said was the following. So here's what he's saying, and it is correct. His argument is correct. So the current was flowing in this direction, and when you're closing the switch, when you're opening the switch, what is happening? This current would decrease. Okay. Since this current is decreasing, this guy will act like a battery trying to oppose that. So this end will be positive, meaning it'll drive a current like this. Okay, let's give Fred a hand. Very good. Okay. All right. Good job, Fred. So what is it that we're trying to calculate?
Current at 0 and then a current at a time.
Oh man, I gotta read this again. Circuit after steady state, which is immediately thereafter. Determine the current through L at t equal to 0. So the steady state current. Okay. So the steady state current. So the steady state is, so in this expression it's 1 minus e to the power of minus t tau, and this is t equal to infinity current. Okay, so I is E over R, which is 20 volts divided by 5 ohms, 4 amps. Okay, that's the steady state current. So the current through IL is, that's part A. Yeah. B, the current through L at t equal to 10 minus 4. Both the resistors are 5 ohms. Okay. Okay, so part B, as Fred tells us, okay, remember this end is positive and the current is flowing like that. Okay, so that's the circuit. And the current through that at 4 times 10, 0.4 milliseconds. If you guys look up for this circuit, the current is I naught times e to the power of minus t by tau. Okay, where tau is the time constant of that circuit, which is L by R. Okay? And let's figure out the time constant for that circuit. So yeah. Okay. What is L is 4 millihenries, and R is 5 ohms. 0.8 into 10 minus 3 seconds, 0.8 milliseconds. Okay. And what we are trying to find is I t, the current at 4 times 10 minus 4 seconds, which is 0.4 milliseconds, which is half a time constant. Okay. The time constant for the circuit is 0.8 milliseconds. All right, so the current at this time is I naught e to the power of minus t by tau. I naught was 4 amps. E to the power of minus 1/2 tau divided by tau. Okay.
So the big part of these equations is to figure out how many time constants the time value they give is worth.
So the language in these things is time constant, and so you'll do exponentials in radioactive decay, in so RL circuits and all that kind of stuff. So this is equal to 2.43 amps. All right, and then there's another part to it. The voltage across L and R at 0.4 milliseconds. Okay. So let me, what part is this? Part C. Okay, so Remember, of course, this was positive, this was negative, the current was like that, and R. So you guys understand, again, if you apply Kirchhoff's second rule, the voltage across this is positive, going from there in the clockwise direction, and the voltage across this is negative. And the voltage across this plus the voltage across this should add up to 0. Okay? So essentially, the voltage across this guy and this guy should be the same. Okay? So the voltage across this guy is L times di by dt. The voltage across this guy is IR minus IR. Okay, so let's I have already written down the signs for this. So this is higher voltage, this is higher voltage. Okay, this is lower voltage. Now the voltage across L is L di by dt minus L di by dt, and IT is I naught e to the power of minus t by tau. So di by dt is I naught times and tau is, so di by dt is minus I naught. Tau is L over R. Okay. And so VL is L times di by dt, which is minus L times minus I naught R by L e to the power of minus okay, so there is VL, and I'll need to add another page. The voltage across R is minus IT by R. And we have VL plus VR. Is this equal to 0? VL is I naught R e to the power of minus t tau, and VR is minus I naught R e to the power of minus t, and that's identically 0. So the sum of the voltages across this plus that is 0 at all times. Okay. Any questions before we move on? I think, is this, oh man, 2 more problems. Let's finish them. I have the recording going, and okay, the lab is short, so, and if anybody has to leave, they can leave. I can just post the problems. Okay, this self-inductance and capacitance of an oscillating circuit are that, respectively. What is the frequency of oscillation? If the maximum potential difference between the plates of the capacitance is 50 volts, what is the maximum current in the circuit? Okay, so, oops. So here's a capacitor, here's an inductor, and this is an oscillating circuit. And Okay. The frequency of oscillation is given by 1 over square root of LC. Okay. So this is the angular frequency, and square root of L is 20 millihenries, and capacitance is 10 minus 6 farads. Okay. So let's take care of powers of 10. This is 10 minus 2, and 10 minus 8, square root of that is 10 minus 4, and that comes to the top, that becomes 10 to the 4. So 10 to the 4 plus square root divided, and that's 1 over seconds. Okay. So this is equal to all right, so that is 7.01 into 10 to the power of 3 radians per second. Okay, so, and if you divide by omega by 2 pi, gives you f, and 2 pi is roughly 6.4, so roughly 1,000 hertz. Okay. So, and what is it? Part B, if the maximum potential difference between the plates of the capacitor is 50 volts, what is the maximum current in the circuit? Okay, so in this, you can look at your notes. Here the charge is varying sinusoidally, so is the current varying sinusoidally. Okay, and you can look up the expressions in your notes. So the charge on the capacitor varies like so. Q max cosine omega t or sine omega t, it doesn't matter. Okay, so and so they give you the maximum voltage. So for the capacitor, on the capacitor, the voltage across the capacitor is equal to the charge across the capacitor divided by C. Okay, and since V max, so V max is equal to Q max divided by C. Q max is Q naught divided by C. Okay. So we are going to evaluate Q naught. Q naught is V max times C, and they give you that to be 50 volts. So you can see that the maximum potential difference between the plates is 50 volts. On the capacitor is 50 volts. So that's 50 volts, and it's 1 microfarad. Okay, so 50 microcoulombs is the maximum, is Q naught. Okay. So now we have Qt as an expression, as a function of time. 50 microcoulombs divided by cosine omega t. And we already have omega from the previous part, from part A. Okay. So now, what is the maximum current in the circuit? So the maximum current in the circuit is dq by dt. The current in the circuit is dq by dt. Okay, so let's add a page. Okay, the current in the circuit is dqt by dt. The negative sign just is telling you about the phase, so that doesn't matter. Okay, so IT equal to, we'll call this I naught sine omega t, and I naught is the maximum current. Microcoulomb times, we figured out omega 7.07 into 10 to the power 3, 1 over second. And so this works out to 0.35 amps. Okay, so that is the amplitude of the current. Oops, that's not what I was trying to do. Okay, so this, what we have found is the amplitude of the current is 0.35 amps sine omega t. Okay, so that's the sinusoidal current in that oscillating circuit. All right. So I'm not going to ask any questions because I just want to go ahead and finish the next problem. Okay. In an oscillating RLC circuit, okay, so this is in the previous problem, okay, so this circuit, if you set up a current in this circuit, it will oscillate forever. Why does it oscillate forever? There is no friction. There is no dissipative element. Soon as you put a resistor kills good energy. It turns good energy into heat. Here in this circuit, energy is being stored only in electric fields and magnetic fields, and it'll oscillate forever. Okay. Now, if you so in this circuit, you have to deal with reality, and with, unfortunately, with, or well, in reality, you have a resistor present. Okay, so, and what you will find is, let's say QT is the charge, and this will I looked up the expression, yeah, 2 over L cosine omega t omega dt. Okay, so, and the frequency changes slightly. Okay, where so that we're not concerned with. The subscript D telling you it's a damped circuit, where omega D is 1 over LC minus R over, you guys will have to look up this. Can you check this expression? So when R equal to 0, it goes back to the normal frequency. Okay. Anyway, so here's what's relevant to us. So you see the amplitude of oscillation is dying exponentially. Okay, and that's what matters to us. And how much time lapses before the amplitude of the oscillation drops to half its initial value? So its initial value is Q naught, and at what time will this become a 1/2 is the question. Okay, so what we want is e to the power of minus RT by 2L to be half, assuming this expression is correct. Okay, and you guys can check this, and if it's not, then I'll fix it later. No, I won't fix it later because this is being recorded. Okay, so anyway, you take the logarithm of both sides minus RT 2L equal to T equal to negative 2L divided by R. So at this time, the oscillation amplitude has died to half its value. Okay. So let's plug in the values. 2, what is L? 10 millihenries. R is 2 ohms. Okay. .69, so 6.9 into 10 minus 3 seconds. 6.9 milliseconds. So after 7 milliseconds, the oscillation amplitude has died to half its value. Okay. And on that note, we